Welcome to this fifth lecture in the series on biochemical engineering, and this is on inhibition. We are continuing on inhibition, which is substrate inhibition. But what we'll do is we'll pick up from, before we go into the details of substrate inhibition, we'll pick up from where we left. And one of the things that we are discussing in the last class was the question of multiplicity, and the fact that there could be, if you have autocatalytic reactions, there could be reactor runaways. So why I'm doing this, and this is connected to both the substrate inhibition and what we're going to study in today's lecture. Where does this multiplicity come in from? One of the things that we have to try and understand is where does this multiplicity come in from? And one of the answers I gave, or comments I made in the previous class, is that it has to do with the, mathematically speaking, it has to do with the the algebraic, certain nonlinear form of the equation. Not all nonlinearities will give rise to multiplicity. So if you are dealing with a reaction kinetics that has quadratic or some other form of nonlinearity that leads to more than one solution. So as we know that most nonlinear equations lead to more than one solutions, right? But are all those forms of interest to us? Are all the forms that lead to multiple solutions are interest to us when we are dealing with reactors? Probably not. The reason being that we are only interested in forms that lead to feasible solutions. So if your concentration, for example, is outside the feasible range, if it's negative or if it's a number that's much higher, for example, your initial concentration, say, is 10 micromolar, and your remaining concentration after 15 minutes or something, or if you get it to be 20 micromolar, obviously doesn't make any sense. So it has to be within the feasible range of operation. And so if we have multiple solutions within that feasible range of operation, then we can have certain kinds of multiplicity behavior. So one of the things that I want to show today is these plots that you see on the screen now. So this is, if this is a concentration, and this is typically known as Damkohler number, okay, which is a measure of the reactor residence time. This could be concentration or this could be temperature, okay. So when you have multiplicity in the system, and we'll do this later in the course a little bit more, so you get a plot of this type, right? This is called bifurcation diagram. Okay. So in the bifurcation diagram, and these 2 points, this is an H-shaped bifurcation diagram. And would any of you have an idea what these 2 points are called? Yeah, but that is different from a reaction engineering point of view. From a mathematical point of view, what are these 2 points called? They are called that is right. One is an ignition point and one is an extinction point. So which one is the ignition point? This one? This? No, but this, you're igniting it here, right? And you're extinguishing here. So you're igniting the solution here. No, but yeah, but the thing is, right, lead to ignition, yeah. So see, the thing is that you may not always trace this path. Between these points, several paths are possible. This could be one of the paths, this could be one of the paths, this could be one of the paths. You see what I'm saying? So between these 2 points, several paths are possible. So this is not the unique path between these 2 points. But what is important is that here you are ignited, you are extinguished, the solution is extinguished, that is, you have the low temperature or the low concentration, and then it suddenly goes to the ignition point, that is, it ignites. The top branch is a ignited branch, and the bottom branch is the extinguished branch. So branch. Okay. So the point of ignition is the point where the top branch starts. Fine. Now, what I wanted to know is, mathematically, would you know what these 2 points are called? This point and this point. No, these are called limit points. Okay, these are called limit points. So this is the simplest form of bifurcation we have. So bifurcation essentially means multiple solutions at one particular value of the concentration. So what I mean by multiple solution is that, so at this, within the limit point, so this is one limit point, this is the one limit point. Okay, so at a particular value of Damkohler number, you have 1, 2 and 3 solutions. Okay, 1, 2 and 3 solutions. Fine. What we'll examine later in this class is some of the questions of stability and so on, and just as a prelude I can tell you that these solution 1 or branch 1 and 3 are stable and branch 2 is unstable. Okay, right. So just as a prelude, but why these are stable and that is why these two are stable and the other one is unstable, we'll do later. But this is the simplest form of bifurcation. Then you can have other kinds of bifurcation. You can have pitchfork, you can have, you know, these island like structures. So if you have an, and this is called an isola. Okay, so it's an isolated branch, so it's called an isola. So when you have an isola at this particular Damkohler number, how many solutions you got? 3 at this particular Damkohler number. 5. So 1, 2, 3, these 3 branches are there. So the isola is there along with the Edge-shaped bifurcation diagram, 1, 2, 3 and then 4 and 5. Okay, so 5 at this point, for example, you have 4. Okay, the one for the tangent to the isola, and then and here again 4, and then here again 3 and then 1. So you go from 1 solution to 3 solution to 4 solution to 5 solution to 4 solution to 3 solution to 1 solution. Okay, so that's how we proceed. So so this is just, you know, I need you to understand this concept, because in standard classical chemical engineering you are not used to the whole idea of, so when we're talking of you know, this as a mathematical concept, that's one thing. Now again, if you come back to this, and here we have the concentration and the temperature. So what were we talking of? We're talking of, in a physical sense, that within the reactor it is possible at a particular Damkohler number for 3 concentrations to coexist. Okay, and that is the origin of multiplicity. Okay, you understand what I'm saying? So in a CSTR, for example, you can have the CSTR for any particular Damkohler number can coexist in 3 different concentration or temperature. So this is temperature. In this particular Damkohler number, you have temperature 1, 2 and 3. Okay, that's one possibility. The second possibility is that the same CSTR, within the same CSTR, these 3 temperatures coexist. Okay, that's another possibility. So one possibility is that the entire CSTR exists in temperature T1 or temperature T2 or temperature T3. Okay, with T1 being greater than T2 being greater than T3. So the entire CSTR could be in temperature T1 or T2 or T3. The second possibility is that within the same CSTR you can have regions with temperature T1, temperature T2 and temperature T3, and that is where these issues of instability, the issues of multiplicity, the issues of reactor runaway come in, because you have, and then I explained, you know, in the other class. So with that, so this was sort of a prelude, and the reason we did that was because substrate inhibition or is a sort of catalysis. It is an inhibition, but you can have a catalyzer also. So it's an auto inhibition or auto catalytic effect. So and that was the basis of all these discussion, and one of the things that we tried to point out through this discussion is that even the simplest reaction, which is going to be exothermic, is an autocatalytic reaction. Okay, so this is not so uncommon, and then you will start to see that what happens in a substrate inhibition, and I'll show you in a minute. So essentially in substrate inhibition, what happens is the substrate can inhibit the reaction by binding to a second site on the enzyme. Okay, so if you have the substrate S, then it can bind. So ES is being formed as a complex, and then it binds to a second site of the on the enzyme to form a complex. What would it be? So S is there, it's already binding to ES, and then the substrate is going to bind to a second site on the enzyme. So what would that be? What would that be? It's very, very similar. Is, as I said, here it's written similar to uncompetitive inhibition. So it's ESS, okay. So the first reaction, as you see here, is same as what you had before. That is E plus S giving ES, right? Reversible, and then ES giving product plus the enzyme, back the enzyme. Okay, so that's there. But there, some of the substrate can bind to a second site on the enzyme. So if the substrate is such that it can bind to a second site on the enzyme, then you have ES plus S giving a complex ESS. Okay. So what's the difference between these two bindings? That is written here, that the second binding does not lead to product formation, only the ES can lead to product formation A, and the second point is it typically has much lower affinity, and it has a much larger dissociation constant. So it's much larger dissociation constant and lower affinity, and that's obvious because once you have one molecule of the substrate binding to the enzyme, it's very obvious that the second molecule will have larger dissociation constant and lower affinity. So this is what happens. Now, it's hard for you, I know, at this point to kind of connect what I'm trying to say here with what I said before. But as we go on and start doing the derivations, which we'll do in the next few minute, you start to see that what the connections are. Okay. So are you sure? Are you good with this? So I'll go on to the next slide. Okay. So in the derivation, what would be my yesterday I discussed in great detail. So what would be my points to look for? First is what are the reactions that attain equilibrium, right? So what are the reactions here that attain equilibrium? What one? ES plus S equals, not both. So the second reaction only attains equilibrium. Now next question was what? Species that attain quasi-steady state. So that is which one is that? Yes. And the last point would be the constraint equation. Okay, so let's quickly write those down. So the first one is reaction 2 attains equilibrium, and you can write the equilibrium relation. Okay, done. So reaction 2 attains equilibrium, so you can have ESS as CES times CS over KD. Second is the quasi-steady state assumption for CES. So there's a typo here. It should be DCES. Okay, not DCE. DCES dt equals 0, which gives you CES equals CE times CS over Km. So what you can do is you can now substitute equation 4 in equation 3, and then you can write your CESS as DCE CS squared over Km. Okay. Do you see that? So this is where the nonlinearity comes in, right? Right? Clear? Because CESS equals DCS times CS over KD, and CS you substitute over here, so you will get DCE times CS square, and that's where the first nonlinearity comes in. Okay. Now, so this is what we got, right? All of you? Okay. I'll go to the next slide. So next point would be the constraint equation. Okay. So what would be my constraint? Equals CE naught. Fine. So CE plus CES plus CESS equals CE naught. So the enzyme in the free form and the two complex forms equals CE naught. Okay. So now we can substitute back what we had in the other two So equations. So CE naught equals. So once you substitute back, you get CE naught equals CE plus this term, or in other words, CE equals CE naught over this term. The denominator contains first order and second order terms of CES. Fine. So what's my rate now? What's my rate? Rate of production of P? simply K2 times CES, right. So, that you can substitute from here, because now you got CE terms of CE naught. So, K2 times CES, which is K2 times CE naught CES over this terms. This is what you get. So, what is different between this rate that we got here and everything that we did before? Harush, what would be the difference between this rate we got here and everything that we have done before? So, yeah, that I already said. So, what? Yeah, but in other words, what that means is that it is not possible to express this in the Michaelis-Menten form. So, this is not Michaelis-Menten kinetics. That is the most important thing. So, substrate, when you have substrate inhibition, it's no longer Michaelis-Menten kinetics. That is what I want you to notice at this point. Okay. So, what do you, if I ask you to kind of intuit, what would you intuit to be, how would the rate go? Like in the Michaelis-Menten kinetics, the rate goes like this, right? So, it has a initial slope and then it reaches a, so this is R versus CS, and so this reaches a R max, right? So, so this is the Michaelis-Menten. What would you think how the how this one would look? Like this? Same, then it will go down like this. Okay. What do you think? Huh? Say that, yeah. Who wants to take a shot? Same? Srikanth? What do you think? You have the rate expression in front of you on the screen here, and all you need to do is, so it's a function of CS, so all you need to do is tell me how this goes as a function of CS. Yes, I think what you said is right. That's how it looks like. So, what is this peak going to be? What is the rate? So, this is the maximum rate now. So, that's the difference. Earlier, the saturation limit, the asymptotic limit that you reach over here was the maximum rate. But now, you have the maximum rate over here. So, this is, let's call this R max hat or something. So, or R max double hat. So, this maximum rate is different. Now, the earlier maximum rate was easy to obtain. How did you obtain the earlier maximum rate? You, in the limit of CS much greater than Km, right? So, you just put CS much greater than Km in the equation and you got it. Now, how do you obtain? Because this is the quadratic form. So, what you have to do is to you have to take a derivative of that and equate it to 0 to get the maximum rate. And what you will figure out is that the maximum rate occurs at a CS value which is equals here equals square root of, okay. So, when you do the take the derivative, equate to 0, do the rest of the algebra, we're skipping that here. There's a little bit of algebra there. So, when you do all that algebra, you'll figure out that your CS equals square root of Km dii. At CS equals square root Km K dii, you have the maximum rate, that is R equals R max. Okay. And the maximum rate itself, when you put that value in value of CS into your R, you get the maximum rate as this number, which is dependent on all the rate constants and C naught. right? So we'll move on. So what I'll show you next is the plot. This is a plot of substrate inhibition without substrate inhibition on top and with substrate inhibition below. So as he correctly mentioned that without, this is a Michaelis-Menten kinetics without substrate inhibition, it goes and actually should saturate, and with substrate inhibition it goes up to a certain point. It's the same. Okay, why is it the same? Can somebody comment on that? Why are these two slopes more or less the same? Then what happens? Right. So when CS is low, then the effect of inhibition is substrate inhibition is not there, because in the limit of small CS, the substrate inhibition, the formula for substrate inhibition that you had, let's go back to it here, will go back to the old formula. Okay, for without inhibition. So with and without inhibition makes no difference at small values of CS, because CS square is very small. So these two lines merge and then they reach a peak which is given at the value of square root of KD11, and then it goes down again and goes to what? What does it go to? So yeah, you can see here, for example, if CS is very large, then it will go to 0, right? Because what was happening was, mathematically what was happening before was that the numerator and denominator were both first order. Earlier were both first order in CS, right? As a result, it cannot go to 0. At large values of CS, it will go to a saturation limit. Whereas here, the numerator is first order in CS, the denominator is second order in CS. So as CS goes to a large number, it goes to 1 over CS and therefore goes to 0. Fine. So this is about substrate inhibition. So we are more or less done with inhibition. So the different kinds of inhibition we studied are competitive, non-competitive, uncompetitive, and substrate. So what we'll do today is a wrap on the enzyme kinetics as we are studying in this class. And the final 2 or 3 things that we're going to look at are, first is the effect of pH on enzyme activity. Okay, so it turns out that the specific kinds of enzymes work within a certain pH range. So you know this. So what is the pH range of the human body? 7.2 to 7.4. Okay, that's a varies depending extracellular, intracellular, and so on. But overall range is 7.2 to 7.4. So as you would understand that many of the enzymes, or most of the enzymes, that physiological enzymes that work in the human system, would have to be active within that range, right? If it's active at 5 or 6 or 8, doesn't make any sense, because the range, the window that we have is that. And enzymes, one of the ways that the specificity of the enzymes work is the pH. So when it's sensitive to pH or sensitive to a certain range of the pH, the enzyme is specific. So if you take the enzyme outside that range, it would stop working. So one of the things that, if you're doing experiments in the lab, is to control the pH using buffers and so on, and keep it within a certain range where the enzyme is active. So what happens when an enzyme is not active, or you go beyond the pH range where it's supposed to be active? So I'll show you this. So this is what happens. So this, what happens is, because of the effect of pH, there's a proton transfer. Okay, so because of the effect of pH, there's a hydrogen ion transfer, and the enzyme is typically assumed to be active in this form, which is a E- form. Okay, and then if there is a hydrogen ion transfer to it, then it can become the E form, which is without the non-ionic form, or it can go to the double ion. Okay, both of which are inactive. So it is active within this range. So essentially that is how pH affects. So excess of hydrogen ion, it will go from the E- to E form. Depletion of hydrogen ion, it will go from the E- to E2- form. Okay, and so it will be active only in that range, in the E- form. So that's how it's sort of. So when I'm trying to figure out, so at any point in, at a certain pH, for example, can you expect the entire enzyme that you put in there to be active? No, right? It's only a fraction of it that's even at a certain pH. So even if you want to, if the enzyme's range is 7 to 7.4, and the pH that you are maintaining in your solution is 7.2, but still 100% of the enzyme is not going to be in the active form. A part of it are going to be in the E form, and a part of it is going to be in the E2 minus form. Okay. So how do we figure that out? How do we figure out how much of an enzyme is actually in this in the active form? So what we do is we assume that these two reactions. So this is the first reaction, which is E going to E minus plus H plus. So E minus is your active enzyme. So a proton is added to it and it goes to the E form, and K1 is your equilibrium constant for this. Okay. The second one is E minus again is your active form, and a proton is taken out and it goes to the E2 minus form. Okay. And K2 is the equilibrium constant for this. Right? Clear? Okay. Fine. So all we go to do is now write the equilibrium relations for these, because we need to figure out that what is the fraction in which these this is distributed. The enzyme is distributed between one active and two inactive forms. So we write the equilibrium relations for these two reactions. Right. So what should we do next? What does the intuition tell us? Huh? What's that? What does the intuition tell us? What should we do next? Take ratios of 2, but what did you do? You can't eliminate. So what do we want to find out? Let's first answer that question. What do I want? What should be my goal? What do I want to find out in this? E minus, the amount of active enzyme out of the total amount of enzyme that is there. What is the fraction of active enzyme? So if you divide one by the other or multiply one by the other, what happens? Nothing happens. If you divide one by the other, the hydrogen ion is gone, but you have all three left. If you multiply one by the other, you got rid of E minus, the one that you want to figure out. So that's not the only solution. That's not the solution essentially. So what other option is there? And you have to take a clue from what we did before. The answer is there. Right. So what is the constraint equation? Right. Very good. So that's what you have to do. So you can take ratios and all that, but the most important thing at this point is to be able to write the constraint equation, which is that the total amount of enzyme that is present is distributed in three forms: the E, that is the E minus, that is active form, and the two inactive form, that is E2 minus and E. Right. So that is what you need to do. So once you do that, then what you can do is, like you did before, is try and express everything in terms of E minus. So now use the equilibrium relation. So express E as a function of E minus, express E2 minus as a function of E minus, right? So you can take E minus out of the parenthesis, and you will have, so E naught equals E minus times this whole number 1 plus H plus over K1 plus K2 over H plus. Fine. So this is your fraction of the total enzyme that is active. Good. So, but H plus is something that I don't want to use in this form. I want to use it in the form of pH, right? So what I do is simply use the definition of pH as minus log H plus, log to the best 10 H plus, and therefore I can just rewrite this this expression that I have over here, y bar, in terms of pH, right? Shouldn't be a problem. So there will be negative and a positive sign. And now before I explain what I wrote at the bottom, let me show you the plot. Okay, so this is how the plot of y bar versus pH look like. Okay, why this plot? Again, so what is there? What do you see there? There is a nonlinearity over here, right, in H plus. So if you take H plus, for example, in the numerator, okay, what happens? In the denominator you get H plus H plus square plus a constant, and in the numerator you get H plus. So again there is a nonlinearity out here, and as a result of which, when you take the fraction, for example, if I take at a certain fraction. I can look at it two ways. So if you look at the line over here, the top line, the horizontal line, at a certain fraction, I obtain, see, it's easy to measure. I can obtain what is the amount of active enzyme that I have in the system. Okay, I can measure that, and at that fraction, I'm trying to figure out from the fraction what is the pH. But the problem is I'm unable to. The reason is this is a repetitive curve. This is a nonlinear curve which has multiple solutions again. And then so at that particular y bar, I can have several values of pH. So this could be one value, this could be another value, this could be a third value, fourth value, fifth value, sixth value, and so on, right? Again, if you look at the other way, at a particular, so this is a vertical line now, at a particular value of pH, if I want to figure out what my fraction of enzyme, active enzyme is, I can have two solutions, right? I can have one solution also, but within a very specific places I can have one solution, like a place like this where the two intersect. But otherwise, typically here I have two solutions. Okay, here how many solutions I got? Three solutions. If I draw the line over here, so 1, 2, 3. Again here 1, 2, 3. So most of the places you'll see I'll have three solutions. In some small regions, windows, I can have two solutions. In some very small windows, I can have one solution. But at the end of the day, this is again a question of multiplicity. So if I give you a particular value of the fraction of enzyme and ask you to find what the pH is, then there are n number of solutions. If I give you a pH and tell you what the fraction of enzyme is, typically there will be, most of the cases, there will be three solutions. Okay, so this is these are the reasons, you know, I talked about multiplicity and bifurcation, because unless you understand that theory, it would be hard for you to appreciate what is going on here. And this would look like Fourier solutions. Now, what is important is that you have to draw your window over here, right? So your window, if it's that is in the physiological systems, for example, if your window is 7.2 to 7.4, then you draw your window over here and try to figure out what your fractions are. But again, in that case, you will get multiple solutions. You can have multiple values of the fraction. So what it means is that even at a certain pH, you can multiple values of the active enzyme can coexist even at a particular pH. So these are some realities that we have to live with, you know, and there is no way to walk around it. So this is the concept of the effect of pH. So you more or less understand how it affects, you know, and a general trend, it's a general trend again, is that it increases with a certain, as you keep increasing pH, then it attains a maximum and then it decreases. But that, as I said, is a very general trend. The reason is that would be a very narrow way of looking at it, because you see these multiple solutions that are there, and as a result of which you cannot make such generic comments. Do you understand what I'm trying to say? So if you take one of these mountains, okay, and then say that as pH increases, the active enzyme increases and then reaches a peak and then decreases, that's a very narrow way of looking at it, because you have these other overlapping mountains, other mountains overlapping with them, so you cannot make a generic comment. So you have to understand this from a broader point of view. Okay, so that's about it with the effect of pH. Well, yeah. So at the maximum, so this value that is attained, the Y max, the maximum value that is there, and that is what you'd like, right, for your system. If you want your system to be not inhibited, if you want most of your enzyme to be in active form, so the maximum value is something that you'd like to attain, and that maximum value is attained at a pH of pK1 plus pK2. So if you are doing experiments and you want to outside the body, so inside the body, of course, you don't have much control over pH, but if you're doing experiments and you want to maintain the pH, then you try and maintain it around a value which is half the pK1 plus pK2. Okay, so which the K1 and K2 being the equilibrium constants for the two reactions which are known. Fine, right? Shall we move on? Okay, next is the effect of temperature, and that's a very easy effect actually. So on the enzyme kinetics. So what happens is, in the effect of temperature, is that the rate constants that you have for enzymes, you know, they just follow Arrhenius kinetics. So K would be the Arrhenius factor times exponentially minus E over RT. So this is a very straightforward thing. But what is important to notice over here, that these enzymes are typically active over a certain temperature range, just as a human physiological body pH we discussed, and the range for that is between 7.2 to 7.4. So the human body also has a temperature range. So what is the normal temperature? How much? 37 degrees centigrade, which is what the body tries to maintain. Okay, so even if you are in a very cold, if your outside temperature is -10, if you are in a very cold country, your body will still try to maintain a 37. That's one of the miracles of the body. So it has all these cooling effects and heating effects, internal cooling effects, internal heating effects, and then so the body will try to maintain the temperature. Well, it cannot always. In this winter itself, probably around 500 people died in India just from cold. So the body tries to maintain that temperature as long as it can, and when it cannot, obviously it gives up. On the other end, you hear during summer people dying from sunstroke. So that's another extremity. So the body can maintain. So 37 is the optimum temperature. It can maintain. It can take temperatures up to 48, 50, where up to say 48 or so, or 50 maybe. Where what happens is that the body tries to maintain. So the internal temperature is always maintained around 37. And if it's not maintained around 37, then what you have, you got fever, right? That's what. But if you look at, say, even when somebody has a fever of 102 or 103, and you take the deviation from 98 or 97.5 or something, you see the deviation is only a couple of degrees. So 37, and you can go up to 39 or 38.5, and then a couple of degrees here. So the temperature range within which the body works is very small. Okay. Now, enzymes obviously would correspond to the temperature. The physiological enzymes, the enzymes that work in the human body, would try to correspond to the temperature range, of course. And if the temperature range is higher than that, it still takes it to some extent. But above 45, and this, some of you, if you're doing experiments with enzymes, you'll figure this out. Above 45 degrees centigrade, the enzymes start to deactivate. Okay. So this, when you're talking of effect of temperature, they're valid within a temperature range. Fine. Now, next thing we look at is the effect of deactivation. So at temperatures higher than 45, we said that it deactivates. Now, what is the mechanism of deactivation? So if I ask you a question, what do you think would be the mechanisms of deactivation, or could be the mechanisms of deactivation? So there will be an enzyme that is in deactivated form, and there is an enzyme that is in activated form, right? So by the way, this is different. Don't confuse it with the inactive form. Inactive form is a form that is right now not active, but can become active at any point of time. So it's not deactivated. There's a difference between the deactivated form and the inactive. So there are two models. Typically, people think of it in two different ways. One is known as the reversible deactivation. The other one is the irreversible deactivation. So in reversible deactivation, you can go to the deactivated mode, and from that you can get back to the activated mode. Whereas in the irreversible deactivation, you assume that you go to the deactivated mode irreversibly, and you cannot get back to the activated mode. Okay. So let's have a quick look at these two models. So the first one is the reversible model. So, and second one is the irreversible model. So the reversible model is something like this. It's a very straightforward thing. That is, activated enzyme goes from the activated form to the inactive form, deactivated form, and so here EI is, the subscript EI is used because it can get back to the activated form, and that's a reversible one. And so the ratio is given by the equilibrium constant, which is related to the Gibbs free energy change of the system for the transfer between these two modes. Okay. And the second one is a lot more straightforward. It's a irreversible form. So straight away it goes from EA to EI. And then the kinetics of it is straightforward. So dEA dt equals minus kdEA, and you can integrate that to get this. So it's a very straightforward thing. Okay, that sort of brings us to the close of this chapter, but we'll continue with enzymes with a little difference. And so let me summarize for you quickly what we did. So essentially, we started with structures of enzyme and so on, and sorry. So yeah, forget this. I think what we did was started with structures of enzyme and so on, and then talked about the Michaelis-Menten kinetics. And so talked about Michaelis-Menten kinetics, and then talked about the quasi-steady state assumption, figuring out how the Michaelis constants are evaluated graphically here, the slopes and the final asymptote. Okay, so and looked at the two asymptotic limits of small cs and large cs. Okay, that's one thing we did, and then we looked at different ways of evaluation using different plots. Then we tried to figure out whether the quasi-steady state assumption is valid, and we established some conditions under which it's valid. So just to summarize, because some of you may not have been there in some of the classes. So we figured out that we may neglect the quasi-steady state assumption, in which case we have to solve this dynamic equation, and then we compare the rate constants of the two processes to figure out if that works or not. Next thing we did was we tried to understand the regulation of enzyme activity using inhibition. And we talked about why we do inhibition, and this I've talked about several times, I'm not going to repeat. And then we looked at the different kinds of inhibition that you have: competitive, non-competitive, uncompetitive, and substrate inhibition. So what it looked like, so these are some of the examples we did. And what it looked like is that for competitive, so in competitive inhibition, if I am to summarize, what happens is that the inhibitor and the substrate, they compete for the attention of the enzyme. So both of them try and bind to the same active site. In next one we did was uncompetitive, I think, inhibition. In uncompetitive inhibition, the enzyme and the substrate do not compete for the same active site. So the enzyme and the inhibitor and the substrate do not compete for the same active site, and the inhibitor essentially binds to the non-active site, another site. Whereas in non-competitive inhibition, this is uncompetitive. In non-competitive inhibition, both these things occur. So the inhibitor binds to the active site as well as binds to the non-active site. And I said this is the most potent form of inhibition because this is what happens. Now, the advantage with this kind of inhibition, non-competitive inhibition, is you can do a couple of things. You can vary both the rate, both the slope and the Rmax and the Km. Okay. In the slope and the asymptote. So what happens in uncompetitive inhibition, if you look at this graph, what happens in uncompetitive inhibition is that the initial slope is the same because the ratios cancel out, if you remember what we did in the last class. In non-competitive, both are different. Okay, then today what we did was substrate inhibition, and what we figured out, substrate inhibition is qualitatively different from other kinds of inhibition. It's an auto-inhibition, that is, the substrate itself inhibits the system, and it's qualitatively different because the earlier kinds of inhibition we looked at retained the Michaelis-Menten form. That is, you had a certain slope, a linear slope, and then you go over and reach a certain asymptote. In substrate inhibition, it doesn't retain the Michaelis-Menten form. It initial slope is still the same, but it goes and reaches a peak, then it comes down. So I'll show you the picture here. And the peak is attained at a certain Rmax, which you can calculate. And then we quickly looked at the effects of pH, effects of temperature, effects of deactivation. So this is this part that we end here, but if you have a quick question, one or two quick questions on this, I'm ready to answer. If there is any, then. If there is none, then we move on. We'll move on to the next chapter. And so what, one of the things that I want to impress upon you after doing all of this is the fact that this enzyme catalysis and enzyme kinetics that we looked at are in which medium, what is the which medium the enzyme is in and which medium the substrate is in, and so on. What phase? What's the phase? And no. the calculations that we did till now. Both are in same phase, right? Yeah. So both are in liquid phase, not specifically not just same phase. Specifically, both are in liquid phase. Okay. So is the Michaelis-Menten kinetics not valid if what he is saying that if one is in solid phase, one is in liquid phase? It is valid. Yeah, it is definitely valid if one is in solid and one is in liquid phase. But there are some other effects that come in. Okay. So if both are in solid liquid phase, for example, then we take into account the reaction. Fine. If one is in solid and one is in liquid phase, the reaction kinetics still remain the same, and what we studied is still good, right? What, in addition to what we studied, what do you need to consider? Say, for example, the enzyme is working on a solid spherical substrate. Okay, the food you've eaten, for example, is trying to digest, or some glucose is trying to break down, or something. Some sugar is trying to break down, for example, and the sugar is in, say, solid phase. And so what would be different now? You don't get confused. I already said that all the reaction mechanism that we studied are all good still. But in addition to that, what phenomena kicks in? Yes, Arush? You've done this in the lab, so you know. If you have sugar and you're trying to break it down using cellulase, and the sugar is in solid phase. So if the sugar is in liquid phase, so the two possibilities, right? You can take the sugar, dissolve it in water, get it into liquid phase completely, and then you add your enzyme into the liquid phase. You can perform your experiments and you'll get results similar to what we showed. Now, if you have the sugar in the solid phase and you add the enzyme, liquid phase enzyme, for example, on the solid phase, what would be different now? Phenomena-wise, what would be different? Yeah, then that's right. Yeah, enzyme is acting. And what else? Diffusion into the substrates. If the substrate is in solid. So two things, both what you said and what you said. So if it's if adsorption is a possibility, if it's a heterogeneous. So when we talk of, so this what happens is, now the title of the next slide that I have over here, and that's a beginning of, not necessarily the next chapter, but it's like a interlude between this chapter and the next chapter and how we connect. So what we studied till now was homogeneous catalysis. Okay, homogeneous catalysis means that both the catalyst and the reactant are in the same phase, right? Are in the same phase and typically in the fluid phase. So that is homogeneous catalysis. Heterogeneous catalysis is if any one of these two is in different phase from the other. Okay, then you immediately it becomes heterogeneous catalysis. It doesn't have to be that both are in the solid phase. Okay, if any one of the reactant or the catalyst are in different phase from the other, then it becomes heterogeneous catalysis. So when it becomes heterogeneous catalysis, then there are other things that kick in. Two things that kick in, and both what he said, one is an adsorption effect, and what he said, one is a diffusion effect, right? So first you're looking at the enzyme on the surface. So if you're looking at the enzyme on the surface, then enzyme is coming and to the surface of the substrate. The enzyme, let's assume that the enzyme is in liquid phase and substrate is in solid phase. It could be the other way around also, but let's assume one thing. So the enzyme comes in and sits on the surface of the substrate. Okay, then it's adsorbed on the surface of the substrate, starts to react. Okay, then post adsorption. So, but this is only the surface, and the substrate is, let's say, a large round body. So it has to diffuse into the core of the substrate. So post that, there is diffusion, right? And then what about the product? These are things you should say, tell me. I shouldn't be telling you, because these are things you've studied in the heterogeneous catalysis, you've studied in reaction engineering. So what are the steps? Tell me what are the steps one by one. No, first adsorption. First adsorption, A. No, first adsorption, then diffusion into the pores, okay. Then reaction, third. Then fourth, diffusion back to the surface, out, and then desorption. So these are the 5 steps. So adsorption first, second, diffusion through the pores, third reaction, diffusion out of the pores, fourth, and fifth is desorption. Okay, this is the mechanism in which it goes on. So here what I'm, this is a simplified form of this, and I will go into much more detail. Today we cannot finish, but starting next class. But this is a simplified form. What have I done over here? I have discounted the two diffusions, the diffusion into the pores, the diffusion out of the pores. Okay, so I'm just assuming that it's not even a porous solid. There's a solid, just a simple case where there's not a porous solid, just a solid on the surface and reaction is occurring, but just a basic of heterogeneous catalysis. Okay, we'll go into diffusion in the next few lectures, make no mistake, but this is a very simplified case where there is no pore diffusion, nothing like that is happening. So this, the solid is here, and the the reactant is coming, and the enzyme is coming and reacting with the adsorbent and forming EA. So this is the adsorption, sorry, it's adsorbing. So this is the adsorption EA, and then EA leads to the product formation. This is a reaction. Okay, so A I use because just to signify that's in a different phase rather than S, and the adsorption is assumed to be in equilibrium. Okay, adsorption is here, it's a reversible form, and then the product formation. Now typically what happens is in most cases it's the adsorption that's the slowest step, not the reaction, because if you look at the rates of adsorption and if you look at the rate constants for reaction, typically in most cases it's adsorption that's the slowest step. So the rate limiting step in most cases is adsorption. Now there is a constraint equation that you can write here as well, like before, and this is, as I said, this is sort of an interlude between the next chapter and the last chapter, and we have not started the next chapter, but just for a sense I'm trying to connect what we did before and what we can do later, is that you can come up with some sort of a constraint equation here as well. And what would that be? One of the things you can tell me very easily, that the total amount of enzyme in the free form and the adsorbed form is a constant. Okay, but rate of product formation, not rate of reaction. Rate of product, if that's a good point. Yeah, so if that's a rate limiting step, then the rate of product formation is the rate of adsorption. Now, as I said before, that the constraint equation could be that my total amount of enzyme in the combined form and this free form is a constant. But if your adsorption is a rate limiting step, would that be the kind of constraint equation you'd want? No. Then what would be a constraint equation? The constraint equation would now be an adsorption, because that's the rate limiting step. See, what is happening is that the number of active sites that it can provide is the rate limiting step, right? So what you want to do is something like this, so what I have on the screen now. So the total sites for adsorption is equals the free sites plus occupied sites. Okay, and the total sites for adsorption for a particular system is known, and so you can have Ca naught equals Ca plus Cea, and adsorption, if that is an equilibrium, then if it's assumed to be in equilibrium, then you can get a relationship between the Ca and the Cea. Okay, fine. And quickly, I have just a minute, so I'll quickly go through this rest. So because this is easy, so once you have understood that, okay, this is a rate limiting step, and then this constraint is going to be an adsorption, so total number of sites equals free sites plus occupied sites, and then you can write the constraint equation that Ca naught equals Ca plus Cea, and you can write the equilibrium relation. So then you can go back like we did last time, go back and substitute the equilibrium relation over here and get a relationship between Ca naught and Ca and Ce, right? And Ka here is the adsorption equilibrium constant, which is the desorption rate constant over the adsorption rate constant. Okay, and the final thing you will get is Ca now, that is, you will get in terms of the free sites, you will get in terms of the total sites and the amount of enzyme. Okay, so I think we'll stop here today, and a little bit is left, but I don't want to hurry you through the thing. So we'll continue in the next class on this, and then move on to the next chapter. Okay, thank you.